In this video, we'll continue our study of solving systems of linear equations. But first, I'll introduce you to Carl Friedrich Gauss, a German mathematician pictured here on the 10-mark note. There's many stories about Gauss that you may have heard before. One, in which he was a kindergartner, he was asked to sum the arithmetic series 1 plus 2 plus 3 all the way up to 100. As a very sharp kindergartner, he already knew how to sum such series without any trouble. Just a few years later, Gauss came up with a proof that any single number that you can think of can be written as a sum of three possibly different triangular numbers. Later on in life, he made many other contributions to mathematics, including developing, as you can see in the picture here, a mathematical formula for the normal distribution. He made other contributions in algebra and astronomy and even non-Euclidean geometry. Believe it or not, Gauss is also given credit for putting on pen and paper the first clear method for solving linear systems of equations. Even though it was known how to algebraically solve linear systems for many, many years before he came around, his method said that if a linear system is changed to another one by any of the following operations, and the operations are an equation could be swapped with another, both sides of an equation could be multiplied by a non-zero constant, or the equation could be replaced by the sum of itself and a multiple of another equation. What Gauss said, if you do any of these things, then the systems will have the same solutions, meaning the system that you started with, and then the system that you created based off of your three operations. You should know that Gauss's method shares some similarities to methods that you've used to solve linear systems. You've probably used substitution and elimination and maybe even graphical methods. Gauss's method is really more than just saying we can apply these three operations. It's about doing them in a way that can be very, very efficient, particularly as the number of equations and unknowns starts to grow very, very large. For our first example, we'll take a look at solving a system of three equations with three unknowns. However, this is not nearly as challenging as most three equation, three unknown systems that you've come across in the past. And that is because the system that we're looking at here is in echelon form. Now, the word echelon, what it really means is an arrangement of troops in a certain way that it's kind of like almost a staircase. So you take a look at this system of equations and how it's arranged from the top left to the bottom right. Each variable is kind of on its own step. And what makes echelon form systems so easy to solve is you can use back substitution. I can look at my last equation here and quickly conclude that z is equal to 2. And if z is equal to 2, I can plug it back into the second equation there and say that negative y plus 2 is equal to 4. And that allows me to conclude that y is equal to negative 2. And once I know that z is equal to 2 and y is equal to negative 2, I can punch them back into the first equation, and that would tell me that 4x plus 4 plus 2, or 4x plus 6, is equal to 8. And if 4x plus 6 is equal to 8, then that means x is equal to 1/2. And I've quickly solved a system of three equations and three unknowns. Now you may be wondering, what does this have to do with Gauss's method? We didn't really use any of Gauss's steps in order to solve this system of equations. But Gauss's method, you'll see, is really about getting every single system quickly and efficiently into echelon form so that back substitution can solve it very, very quickly. Let's take a look at another example. In this example, we see another system of three equations and three unknowns. However, this system is not in echelon form. So what we'll do is we'll begin to use Gauss's steps in order to put it into echelon form so that we can back substitute and solve. As a first step, one thing that you might try is swapping the first equation and the third equation. Now this may seem like a bit of a throwaway kind of step here, but one reason that I like to do it is I like to get a 1x in that top leftmost position. It tends to make the rest of the problem much simpler. So if you're going to use a row swap and you want to communicate it to whoever is reading your work, you might show it kind of like this. I'll use the Greek letter rho and put a subscript 1 to be the equation in row 1, and I'll just indicate that it's being swapped with row 3. Row 1 is swapped with row 3. So use the Greek letter, it looks like a little p, row 1 swapped with row 3. For my second step, I will begin to create that echelon or that staircase form. So what that means is all of the variables that I see below the x that's highlighted in yellow, I want to wipe these out. And if you recall, Gauss says we're allowed to take an equation and replace it by the sum of itself and a multiple of another equation. So my plan is to take equation 2, x minus y plus 2z equal 4, and replace it by the first equation, minus x minus y plus 2z equal 4. So here's what that would look like if I were to try to denote it so someone could follow along. I would say that I'm going to take equation 1, or that's row 1, minus equation 2, row 2, and I'm going to put that in where equation 2 used to be. So mathematically, what that would be is taking, well, leaving x minus z equal 5 right here. First equation is getting unchanged, leaving the third equation unchanged, 2x plus y plus z equal 5. But the change in row 2 is x minus z equal 5 minus x minus y plus 2z equal 4, which of course would just be y minus 3z equals 1. And you can see I'm beginning to create that staircase pattern. My next step would be to try to wipe out the 2x using a similar strategy. And so I will take row 1, or equation 1, multiplied by 2, so that I have 2x minus 2z equal 10, and then subtracting row 3 and placing that in where row 3 was. Again, using Gauss's strategy of taking an equation, replacing it by the sum of itself and a multiple of another, sum or difference, of course. And now my system is starting to look like echelon form. X minus z is equal to 5, y minus 3z is equal to 1. And then if I take 2x minus 2z equal to 10 and subtract 2x plus y plus z equal to 5, I'll get negative y minus 3z is equal to 5. And so I can repeat that exact same idea of replacing equation 3 with the sum of itself and a multiple of another equation. In this case, I'll take equation 2 and add it to equation 3. That'll eliminate the minus y that I see down here and put it completely in staircase form. So equation 2 plus equation 3, I store that in row 3. And my system will become x minus z equals 5, y minus 3z equals 1, and then lastly, negative 6z is equal to 6. And this tells me through back substitution then that z is equal to negative 1. Plugging negative 1 back in, I get y plus 3 is equal to 1, which means y is equal to negative 2. And then plugging negative 1 back into the first equation, I find that x is equal to 4. So the solution to this system as an ordered triplet is 4, negative 2, negative 1. It's worth pointing out that this might not be the fastest way to solve this particular system, but it is very, very systematic. And systematic is very important as the number of equations and unknowns grows larger and larger. Before we get to those larger systems, we should take a moment to explain what's happening visually when we employ Gauss's method of row swapping, multiplying one equation by a constant, or replacing an equation with the sum of itself and another equation. We should see what it looks like visually to understand why his rules work. So to do so, let me graph the system x minus 2y equals 10 and 3x plus y equals 9. So to fit on this tiny little graph paper that I provided over here, I'll let each grid line represent 2. So the first equation, x minus 2y equals 10, that would have an x-intercept of 10, 0, and a y-intercept of negative 5, 0. So remember, each grid line is just going to be 2 units. So if I connect the dots there, I can see the equation of the first line, x minus 2y equals 10. The second line, 3x plus y equals 9, well, that has an x-intercept of 3 and a y-intercept of 9, again, with each grid line representing 2. If I connect the dots there, I can see where these two lines intersect. I can try to eyeball the solution. It looks to be maybe 4, negative 3. And if I substitute 4, negative 3 back into both the first equation and the second equation, I can see that that indeed works. What happens to this system visually as I employ Gauss's method? Now, one thing Gauss says that you can do is that you can swap rows, or you can change the ordering of the equations. I won't do that here, but I will point out then the visual is going to be exactly the same. The first line will become the second, and the second line will become the first. If instead I think about taking the very first equation and multiplying it by a 3, for example, to produce 3x minus 6y equals 30, I still won't be changing the graph at all because the x-intercepts and the y-intercepts of that equation will stay exactly the same. So does anything change visually as you're employing Gauss's method? Well, what if we were to take 3 times the first equation, so that I have 3x, and then subtract the second equation and replace the second equation that is listed there with this result? In that case, my system of equation will become, well, still be x minus 2y equals 10, and I'll still have that very same first line right there. But the new second equation will be negative 7y is equal to 21. And in graphing the equation negative 7y equal to 21, I recognize that that is the same as y equals negative 3, which is a horizontal line right through negative 3 right here. And we can see that it's intersecting our first line in the exact same spot. And this is the idea behind Gauss's method, that the solution is staying the same, even though the lines themselves are actually kind of changing. So Gauss's method could stop right here, but it actually could go a little further. Suppose for a second that I did write that second equation as y equals negative 3. I'll just do some quick erasing here. So it becomes y equals negative 3. I could continue another step in Gauss's method, and I could add 2 of the second equation to the first equation and put that in the first row where the first equation was. That means I can add 2y equals negative 6 to x minus 2y equals 10. You might wonder at first why you would do that, but if you think about it, that would give your second equation, that would be y equals negative 3, and your first equation would be x, and the negative 2y and the positive 2y would cancel each other out, so it'll just be x equals 4. So we've gone a little further than just simply echelon form. We've gotten to the point now that both the x and the y are isolated. And notice when I think about this graphically now, I have a vertical line at x equals 4 and a horizontal line at y equals negative 3, and they're coming together in the exact same spot for negative 3 as the original system. And this is the idea of Gauss's method. Isolate the system to a point that is very, very, very easy to solve. And all you're doing is changing the slopes of the lines, but you're not changing where the lines themselves intersect. Now that we have a good visual of what it means to solve systems of equations in 2 dimensions, we're ready to go into higher dimensions. But first, we should talk about what to expect when solving linear systems. A linear system can be consistent or inconsistent. A consistent linear system has one solution or infinitely many, while inconsistent systems have no solutions. Notice that linear systems cannot have 2 solutions or 7 solutions. It's either 1 or infinite. while they could also potentially have no solutions. Visualizing these possibilities in 2 dimensions is pretty easy. When I'm thinking about a system of equations with exactly one solution, I'm thinking about red and blue lines intersecting in a particular point. This would mean one solution. On the other hand, I might have one line and then another that are exactly the same, and this would be the infinite case. Both the one and the infinite fall under the term consistent. Meanwhile, inconsistent could be maybe a line like that one and another line parallel to it, meaning that the 2 lines never intersect. And that would represent no solutions, or an inconsistent system. What does this look like as we move into higher dimensions? As we move up to 3 dimensions, it's important to know that our equations look like ax plus by plus cz equal d for some constants a, b, c, and d, and some unknowns x, y, and z. The unknowns x, y, and z are the 3 dimensions that I'm referring to. Now, an equation like this, ax plus by plus cz equals d, will not graph a line. Instead, it'll graph a plane. A plane is an infinite flat, almost sheet of paper type thing like you see in the pictures here. When we have 3 planes all graphed at the same time, a whole bunch of different things could happen. It's very possible that we have a case like this one right here, where we lead to just one solution, and that one solution is indicated by this single point here where the 3 planes all collide at the same time. It's also possible that the 3 planes can intersect in a line of solutions like I see in this case. This time we have infinitely many solutions that are all along this line. So we do have consistent systems of 3 equations and 3 unknowns. But we also have inconsistent possibilities, and there's more inconsistent possibilities than you may realize. It's possible that all the planes are parallel, like you see in this picture here. 3 parallel planes never intersect, and therefore they have no solutions. That would be inconsistent. It's also possible that we have some of the planes intersecting, as we can see in the picture on the top. When you take the planes pairwise, you see a line of solutions, but there are never any points where all 3 planes collide. And that's the same for the picture on the bottom, where the blue and the greenish plane are both parallel and the orange plane appears perpendicular. So orange intersects green and orange intersects blue, but blue will never intersect green. So it's important to know that as we move into higher dimensions, what we said about 2 dimensions is still the same. We can have consistent and inconsistent systems. Consistent might mean one solution, or it might mean infinitely many, and inconsistent is always going to mean no solutions. Now, the way in which you reach no solutions might be a little different, but if there's no solutions, then there's no solutions, and there's not a whole lot more to say. In this example, we're given a system of 3 equations with 3 unknowns, along with a couple constants that we don't know, a and b, and we're asked to determine the value or the values of a and b for which this system is consistent and independent. Independent, I should point out, means that there is one and only one solution for x, y, and z that works. Pause the video and see if you can use Gauss's method to put this into echelon form. Once in echelon form, see if there's any insight that you can use to figure out which values of a and b make it both consistent and independent. Here I've shown my steps in Gaussian elimination. For the first step, just to illustrate, what I did was I took row 2 and I subtracted 3 times row 1, and I put that into row 2 right here, because what that did was it eliminated the 3x from the conversation. For the second part, I left row 2, or equation 2, and equation 1 alone, and I manipulated equation 3. I manipulated it by taking equation 3 as it was currently written, 2x minus 4y plus az equals b, and I subtracted 2 row 1s. I think now you can probably start to see why I like to have that 1x in the top left position, because I can always quickly use it to manipulate the other rows. So I did this and I put it into row 3. And then what I wanted to be able to do was eliminate the negative 2y down there so that I'm in echelon form. And I did that by taking equation 3, which had a negative 2y, and adding 2 equation 2's and put that in row 3. And I got to this point right here. And so now I can see how the echelon form of this particular system of equations can help me answer this question about what are the values of the a and b for which the system is consistent and independent. Will any value of a and b work? Are there only particular values of a and b? Well, what it really comes down to is this third equation right here. A plus 4 times z is equal to b minus 4. If I can solve this equation for z, then I can back substitute the solution for z into this second equation and find a solution for y. And then I can back substitute the solutions for y and z into this first equation and find a solution for x. So when can I solve the quantity a plus 4 times z equals b minus 4? And when can't I? Well, most of the time you can. If a equals 1 and b equals 7, you're in good shape. If a equals 10 and b equals 132, you're just fine. There's one real problem that you can run into. If a is equal to negative 4, then I have an issue. If a is equal to negative 4, then the left-hand side of this last equation is equal to 0. And what that means is I will not be able to solve for z. And if I can't solve for z, any particular z, I can't back substitute it into equation 2, and I can't back substitute those answers into equation 1. So to answer the question, the value or values of a and b for which this system is consistent and independent is most values. The only ones that don't work, so we can have any a and b with the exception of a equal to negative 4. B can actually be anything it wants, but A can't be negative 4. A can be almost anything it wants, just not negative 4. You may have been left wondering from that last example, what about other possibilities? Which values of A and B, for example, will make the system inconsistent? That question is actually rather simple to answer. Let's bring back our work from last time, where we put it into echelon form. Now, I like to think about inconsistent systems as contradictory systems, or systems that contain some bit of nonsense. So imagine for a second that A did equal negative 4, so that the left-hand side of this third equation was 0. What must B be equal to in order to create nonsense? Well, if, for example, b was equal to 5, then the right-hand side would be 5 minus 4, or 1. And this clearly would be nonsense to say that 0 was equal to 1. So the answer to our question, the values of a and b for which the system is inconsistent, would be when a is equal to negative 4 and b is anything other than positive 4. In this example, we're asked to solve this system and express the solution using a parameterization. What that's implying is there is not one unique independent solution to this system. However, the system is consistent. It's just consistent and has an infinite number of solutions. If we're thinking about it visually, this problem involves 3 planes intersecting in 3-dimensional space in a line. And that line we're going to describe using a parameterization. So to get started, what you should do is try to reduce this system using Gauss's steps to echelon form. Pause the video and give it a try. Here I've shown my first two steps toward putting this system in echelon form. In my very first step, I did the simple swap row 1 with row 2, and that was simply because I like to have a 1x in that top pivot position. In the second step, what I did was I took equation 2 right here, and I wanted to eliminate the 2x in equation 2. So I subtracted 2 of equation 1, and I placed that result into equation 2, or where row 2 was. I want to repeat that process again, but this time I would like to eliminate the 3x down here. Notice that when I do that, something interesting happens. When I do row 3 minus 3 row 1s, I end up getting 3x minus x, which is 0, negative y minus 3 negative y's, which is 2y, 0z minus 3 negative z's, which is 3z, and 4 minus 3 1's, which is 1. That is to say, I get an exact replica of what I already have in row 2, but now it's listed in row 3. 2y plus 3z equals 1. And that tells me that in my next step, all I would need to do is take row 2 and subtract row 3, or add negative 1 row 3's to it, and place that into row 3 in order to have 0 equals 0 as my third equation. In other words, I found a redundancy. I don't really have 3 equations and 3 unknowns, but I really only have 2 unique equations with 3 unknowns. And that's why, visually speaking, I have a whole line of solutions. In order to describe that line, we can use a parameterization. That could look like this. We can describe all 3 of our variables in terms of the same variable. So we can describe x and y and z all in terms of the same variable. I'll call that variable t, and I'll start by setting it equal to z. But there's a lot of different ways to write a parameterization. And so if z is equal to t, then I can see in my second equation here that 2y plus 3t is equal to 1. That is to say that 2y is equal to 1 minus 3t, or y is equal to 1/2 minus 3/2 t. So y is now described in terms of t, just like z is. And then going back one step further, I can see that x is equal to y plus z plus 1, where y is equal to 1/2 minus 3/2 t, and z is equal to t. X is equal to that. And so, collecting all of the like terms, I find out that x is equal to 1 plus 1/2 is 3/2, and negative 3/2 plus 1 is negative 1/2. So 3/2 minus 1/2 t. And this is my parameterization that describes all possible solutions. If you prefer to write it as an ordered triple, you could write it as 3/2 minus 1/2 t, comma, 1/2 minus 3/2 t, comma, t. And if you'd like to think about what a particular solution might look like, you can pick a value of t. For example, when t equals 1, my ordered triple would be 3/2 minus 1/2, which is 1, 1/2 minus 3/2, which is negative 1, and then just 1. So here is a particular solution to this system, and you can plug it in and you can see that it works. 2 times 1 plus 1 is 3, 1 minus negative 1 minus 1 is equal to 1, and 3 times 1 minus negative 1 is equal to 4. But you can also think of all of the different solutions, all infinity of the solutions. They all take on that form, 3/2 minus 1/2 t, comma, 1/2 minus 3/2 t, comma, t. Here's another example of solving a system in which the solution is consistent but dependent. What that means is we don't have just one unique solution, but we have an infinite number, and all those solutions lie along some line, and we'd like to describe that line using a parameterization? Well, you can almost see when this is the case. In other words, sometimes you can look closely at your system of equations and you can tell exactly from the system rather than the directions that we have some redundancies. What I mean by that is some of the equations don't offer any new information. For example, just imagine you took equation 1, there's row 1, and you subtracted 2, equation 2. Well, then you'd have x minus 0, that would be x. You'd have 2y minus 2y's, that would be 0y. And you'd have 0 minus 2z's, and that would be 2z. Well, that looks a heck of a lot like what you're seeing here in equation 3. It works for the right-hand sides as well. And that tells me that this equation is redundant. It offers no new information. You can use Gauss's steps in order to eliminate it entirely, so that you're left with nothing but x plus 2y equals 4, y minus z equals 0, and a third useless equation of 0 equals 0. And this is precisely when you'd have a whole line of solutions. Now we can describe those solutions using a parameterization. So x, y, and z can all be described in terms of some other variable. If we let z equal to t, then the second equation right here tells me y minus z must be equal to 0. That means y must also be equal to t. Going back to my first equation, x plus 2y is equal to 4. If y is equal to t, then that means x is equal to 4 minus 2t. And this describes all possible solutions to this system of equations. One possible solution when t is equal to 0, x is 4, y and z are both 0. Another possible solution when t is equal to 1, x would be 2, and y and z would both be 1. Another possible solution when t is equal to 2, x would be 2, and x would be 0, and y and z would both be equal to 2, etc., etc. All solutions that take this particular form would solve this system. In our last example, we're asked to solve a much larger system than we're accustomed to, a 4x4, 4 equations and 4 unknowns. However, our work's going to be a little easier than any old 4x4 because we're asked to express the solution as a parameterization, which is implying that some of the equations might be redundant. Pause the video quickly and see if you can identify which equations in this system are redundant. That is, they don't offer any new information from equations that have already been presented. If you said that the fourth equation was redundant, good for you. You can see that it is exactly equation 2 multiplied by a minus 1. However, did you notice that the third equation is also redundant? You can arrive at the third equation by taking 3 of equation 1 and subtracting from that 3 equation 2. If you didn't notice this fact, don't worry. It's nice to know that Gauss's steps help uncover any redundant equations. And what that means is the system that we have right here is already in echelon form. It might not be obvious when you first write it out that it has that nice staircase quality to it. However, you see that when you write it out and you leave out the equations at the bottom, you have a pivot in that first position and there's no variables below it, and then another pivot in that second position and no variables below it either. There's a very simple looking staircase. In this staircase or echelon form, we can give some special names to different variables that show up in different ways. For example, you notice that x and y form the steps. These two variables are often called pivots. These are your pivots. If I had a third equation down here that was like z equals something something, then z would also be a pivot. But I didn't. I ended up with a 0 equals 0 down here, and so I'll just erase that. But then that remains, what are z and w if they aren't pivots in this equation? Well, z and w are referred to as free variables. What that means is you can choose z and w freely, and then x and y are determined by them. And that means that z and w are the variables that will set parameters equal to in order to define x and y. And I can do this right now in this particular step. I can let z equal t1 and w equal t2. However, I like to take one additional step. When I have a pivot like x or like y, I like to be sure that the column that that pivot's in is entirely clear, not just below, but also above. So I see, for the case of x, that x's column is entirely clear below, and there's nothing above x, so that one's good. Meanwhile, y, the column is clear below, but it's not clear above. I'd like to clear that out before I write my parameterization. You'll see that this makes writing the parameterization very, very simple. So I'll take one more step, one more Gaussian elimination step, and that step will involve taking equation 1, subtracting from it equation 2, and writing that where equation 1 once was. So equation 2 is staying exactly the same, y minus z plus w equals -1, but equation 2 will become x. The y will clear out because you'll have y minus y. Then you'll have z minus -z, so that'll be plus 2z, and then -w minus 2w, and that will equal 1 minus -1, so a 2. Okay, I prefer, and it is a bit of a matter of preference, I prefer this form for writing the parameterization. And here's why. When I'm looking at that form and I want to describe x, y, z, and w, all in terms of some parameters, I start with my free variables, z and w. I'll let them equal t1 and t2, or whatever letters you like. And then I can look at equation 2 right here, y minus z plus w equals -1. And I can mentally substitute t1 and t2 and isolate the y and see that that becomes -1 plus t1 minus t2, like that. And then I can look at the first equation. Maybe I'll make it blue, x plus 2z minus 2w. And I can mentally substitute t1 and t2 in for z and w and isolate the x so that it becomes 2 minus 2t1 plus 2t2. And now I've written my parameterization. If I don't take that extra step and I try to jump right to the parameterization, this y right here that's highlighted in yellow becomes kind of annoying, and it relies a little extra algebra, and it's hard to do it just mentally. You end up having to scribble a few things on the side. That extra step goes from what is called echelon form to row reduced echelon form. And we'll talk more about that in a future video.